2.8 is on Picard's method. So this is objective 3. Okay, what do we do if we want to solve a differential equation, but we don't know how? It doesn't fall into any of the categories that we've learned so far. You can use Euler's method to approximate a solution. Okay, Picard's method is another way to approximate a solution. So that's what we're going to do. Here's the idea with Picard's method. You're going to have some initial value problem, y prime equals f of xy. So y prime is some function in terms of xy, and then you're going to be given the initial condition. Okay, so what you're going to do is you are going to integrate with respect to x. When you do that, integrating y prime, you're going to end up with y of x. On the right side, you're going to end up with a constant, and then you're going to have to integrate this. Now, the notation changes a little bit. You're integrating with respect to x, so this is really going to be f of t, comma, y of t, dt, integrating from your initial condition to x. Now, do we recognize that when I do this, this is going to end up being an expression in terms of x? So this is going to be some number, that is just going to stay x. So when you integrate, this will be in some expression in terms of x. Then we have that initial condition. So using that, we get y of x sub 0 equals c plus x of 0 to x of 0, right, because I'm replacing x with x sub 0, of f of t, comma, y of t, dt. Now, if lower bound and upper bound are the same, that's really 0. So this tells us that our c is really y sub 0, our initial y. So now what we have is y of x equals y naught, add the integral of x of 0 to x of f of t, comma, y of t, dt. Okay, so then here's the idea with Picard's method. We're going to use a method of successive approximations. So we're going to try to approximate better and better and better. Is this pen okay, or would you all prefer that I write in marker? Okay, perfect. So here's the idea. We are going to suppose that y sub 0 of x is a continuous function that represents a guess to the solution. So we're going to take a guess as to what the solution is. Here's the idea with successive approximations then. You're going to start with this solution that you think is a guess, or that you are going to guess to be the solution. Then you are going to find the next y. So that's going to be a better approximation. That's going to be the y value that you started with, and then you're going to integrate from x of 0 to x, f of t, comma, y sub 0 of t dt. We hope that this approximation is better than our initial guess. Then you're going to find y sub 2 of x. And that, again, that's going to be y of 0, because that was our c that we found before. Then you're going to integrate again from x of 0 to x, f of t, this time y1 of t dt. So you're going to find all these approximations, y1, y2, y3 of x, etc. You're going to find all of these. You'll be told to stop eventually, so you're going to stop at yn of x, which will be y sub 0 plus x of 0 to x of f of t, comma y of n minus 1 of t dt. And these will be approximations for the solution. Now, I think it's easiest just to do an example, so you see exactly what I'm talking about. First example, consider the initial value problem. Y prime equals y minus 1. Initial condition, y of 0 equals 2. Thank you. Now, could we solve this? Do we know how to solve this? Yes, we definitely do.
Yeah.
Rachel, what's one way that we could solve this?
We can, I guess, separate variables.
Yeah, I would separate it. Yeah, it's separable. Now, we're gonna demonstrate Picard's method just to show you how it works. You are finding y1 all the way up to y4. Okay, so here's the idea. That 0 is the initial x. That 2 is two things. It's the initial y. It's also what we generally choose for y0 of x. So this is our initial guess. Okay, so we're eventually going to need this f of t, comma y of n minus 1 of t. That's going to be y minus 1. So y of n minus 1 of t minus 1. So our general approximation then, our y of n of x, is going to be y sub 0, which is 2, plus integrating from x of 0, so 0, all the way to x, of that f of t y of n minus 1, so that's this. Okay, so we're going to find y1 of x first. It'll be 2 plus 0 to x. If I'm finding y1, I'll be integrating y sub 0 of t minus 1 dt. Y sub 0, we decided, is what we started with. So that'll be 2 minus 1 dt. So this will be 2, and then integrate from 0 to x of 1 dt. So our y1 of x is 2 add x. Okay, so again, the idea, we initially guessed that the solution is 2. Now we have a solution of 2 plus x, which is a little bit better than our initial guess. If we find y of 2, that'll be an even better solution, or an even closer solution. So y2 of x is always going to be the y that you started with. You're still integrating from 0 to x. And then you take the previous y and subtract 1. So you're going to take 2 plus t, in this case, minus 1 dt. So this is 2, and then integrate from 0 to x of t plus 1 dt. So y2 of x then, this will be 1/2 x squared plus x plus 2. Okay, I told us to find y3 and y4 also. So y3 of x is going to be 2, and then integrating from 0 to x, the previous y, so this one right here, that 1/2. It's in terms of t though. T squared plus t plus 2 minus 1 dt. Do you all trust me if I tell you what that ends up being? Okay, it ends up being 1/6 x cubed, add 1/2 x squared, add x, add 2. Anything that you're noticing? Like anything that's interesting? It's going to relate to that, yes. Yeah, do you see that 2 plus x showed up here? And then all of this y showed up here? Okay, so that's what should be the case. So y4 of x then is going to have all of this, and then probably another term. So this one will be 2, and then integrating from 0 to x of the previous y, so 1/6 t cubed plus 1/2 t squared plus t plus 2 minus 1 dt. If you trust me, I will tell you that y4 of x ends up being 1/24 x to the 4th, and then add that 1/6 x cubed, 1/2 x squared, plus x plus 2. Okay, now you're probably wondering, why would I bother doing this? Where is this going? You're not going to keep going forever. You're looking for a pattern. So let's try to find the pattern. If we were to go up to n, whatever n is, we're going to have 2 plus x plus 1/2 x squared, add 1/6 x cubed, add 1/24 x to the 4th, etc. This is the same as 2 add x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, so we get y sub n of x is 1. So if I take a 1 away from here, I then will have the sum from k equals 0 to n of x to the k over k factorial. If I take the limit as n goes to infinity of all of that, I'm going to get 1 plus, what is this? What is that the expansion for? Do you remember doing series expansions last year?
No, I have a question.
Mm-hmm.
Why is it 1 plus instead of 2?
Because I need to take a 1. The series expansion I'm looking for is 1 plus e to the x.
Oh, yeah.
So this is possibly our solution then. What time did I tell you all to stop me? Okay, look, that's so great, because now what we can do is solve the initial value problem and see if this is actually the solution. Okay, so what I'm going to be looking for, I don't expect you guys to have all of these memorized. You're going to have to look them up. So the book is going to have you find y1, y2, y3, y4, and then probably give the series expansion. So you can look those up, that's fine. On a test, I will ask you to get to this point. So I will ask you for y1, y2, y3, y4. Okay, let's actually solve this to see if we do get 1 plus e to the x. Like Rachel said, this is separable. What is going to be my first step? Okay, separating, yes.
Write as dy dx.
Sure. What? My real question is, what am I separating? What am I moving to the other side?
The y minus 1.
Y minus 1, not just y. So you're going to divide by y minus 1. You get dy over y minus 1 equals dx. If I integrate both sides, this will be the natural log of y minus 1 equals c, equals x plus c. If I raise both sides to e, I'm going to end up with y equals c e to the x plus 1. This is really c1. We were also given the initial condition of 0, 2. So we get 2 equals c1 e to the 0 plus 1, which tells us that c1 is 1. So we get y equals e to the x plus 1. So using both Picard's method and solving, we still get the same solution. Now, you're not always going to end up with a nice series expansion like e to the x. Do we get the idea of Picard's method? Okay, you only have 2 problems like that on tonight's homework. So that should take you maybe 6 minutes.